is the relationship U V1 as that's a really crucial relationship. It tells you how this is the fine parameter or the geodesic fine parameter separation between C0 and C1 along C. Okay? That's this distance here. Look at the fine parameter along the geodesic, the null geodesic that crosses C0 and C1, and that's along this geodesic C, that's lambda 0 minus lambda 1, lambda 0, 0. If you would use the minus the fine parameter separation. V0 minus V1 is the same thing, same along scry minus. You're looking at the null geodesic and scry minus, looking at the fine parameter along that null geodesic, distance between C0 and C1, and that fine parameter, that's V0 minus V1. U equals V1 is this value here. That's the value of U that corresponds to the reflection at R equals 0 of the null geodesic that came in along V equals V1. So it's telling you how, as lambda 1 goes to 0, so as C1 approaches the null generator of the horizon, C1 approaches C0, which is the null generator of the horizon, U will diverge because U goes to infinity. And it will diverge in this way, logarithmically. And logarithmically, more importantly, logarithmically with V0 minus V1. This value here will go to infinity logarithmically with a fine parameter separation between C0 and C1 here. That's the crucial thing. That's what will give rise to the fact that log-relation is terminal. And as I mentioned, there's a similar relationship for the real observers. Log, or the reverse of this exponential type of relationship. Between those two types. Okay, and then we constructed the modes, phi modes. So phi modes were defined in this way. And these guys, phi, have got coefficients A's, and that gives an vacuum state. And we can do the same thing here. We can define some out modes. Let me do this. Oh, okay. the out modes. We've got the outs annihilation operators, and so. And we want to relate the out vacuum state and the in vacuum state. The out vacuum state is a Minkowski vacuum state, that's chi plus. The in vacuum state is a Minkowski vacuum state, and it's chi minus. It's chi minus and chi plus are flat. And remember, this is defined as chi minus, which is a Cauchy hypersurface, or characteristic initial data surface. This is defined as chi plus, which is not a characteristic initial data surface. You need to include the horizon to get a characteristic initial data surface. So the phi outs are 0 here. The phi outs are 0. So they are purely outgoing and chi plus. They are 0, have 0 Cauchy data on H plus. So we need to define some other modes. I think we're calling Q's, Q lambdas. And they play no role. They're not going to play any role, whatever they are. So they have 0 Cauchy data on chi plus. And they are, whatever they are, they're such that these two guys together form a complete set. So we want to find the Boggle of transformation between the two asymptotic vacuum states to see if starting with an empty vacuum as chi minus, well, we get particle production as chi plus. So what we really want is to find the relationship between the outs and the ins. And there will be particle production if any beta is non-zero. We saw this in the channel formalism. And they're equivalent back here if the betas are all zero. Just to note, I think I made a typo one. I chose a normalization, so I defines, I said like we go like this. And it's chi minus. And these are, you can find them. Normalize with the Klein-Roth and scalar product defines. And, well, first of all, I said that this guy was proportional. I think I said PL theta exponential of I and phi, and so that YL minus M was complex conjugation, so that complex conjugation and changing n to minus m just left things invariant. Now, I made a little mistake, which is I did not include an m here. And in fact, these guys are normalized in a way that whenever you send standard normalizations for the Legendre functions, or such that whenever you change m to minus m, there is a change of sign here. So I missed I missed this. This plays no role. It's just an arbitrary phase, choice of phase in the normalizations of the spherical harmonics. Now, I want to be, well, I'm choosing the standard normalization for the spherical harmonics, and so I'm including this. There's nothing wrong with what I did, it just wasn't a standard normalization. So let's choose standard normalization, be consistent throughout. And what that means is the phi, whenever you expand it in terms of the phi inches. And remember, I unfold the minus infinity and infinity to a positive, an integral over the positive frequencies. So this is what I did. And then I used this symmetry. So the similar symmetry for the radial solution, for the boundary condition of the radial solution, for the ODE, and therefore for the radial solution everywhere at any point in space. So I said that this was phi in convex conjugate L M omega, and so because I wanted phi to be real, I chose the ANs, I imposed the ANs, A int, the condition that this is this. With n to minus n. Now, I missed the minus 1 to the n, or I chose a different normalization, a non-standard normalization. Let's choose standard normalization, so let's include the minus 1m here. And so all you have to do is include minus 1m here. Okay, so this is what's different with respect to what I did yesterday. And everything else just carries over, carries through just the same way. Any questions? Okay, let's calculate the betas. We want to see if they're zero or not. So, this is from the general formalism. Lambda bar obviously is just L bar, N bar, omega bar. So we want to calculate these things. We're going to have the Klein-Gordon product. And we don't have an exact solution for phi in and phi out everywhere in spacetime, but we do at sky minus and sky plus. Now, we know phi in at sky minus, we know phi out at sky plus. We have to choose a Cauchy surface here. There's a Klein-Gordon product, which is the integration over a Cauchy surface. You can choose whichever one you want. If we choose sky minus, we need to know phi out and sky minus. So that's what we're going to. We know that sky plus. We need to find what it is at sky minus. So this is what we're going to do next. Let's find the value of phi out and sky minus.
But sky plus isn't a Cauchy surface.
No.
So can you use it as a Cauchy surface to calculate the betas?
No, you have to choose sky plus and H plus. So that's precisely why the choice of Cauchy surface that we take sky minus. If you wanted, you could choose, make your life a little harder. Choose sky plus and H plus. Then you need the Q's and things things get a little messier. You can choose something in Twitter as well. Choose surface. But you don't know the values of phi in and phi out there, so.
The phi out modes are going to scribbles, but they are going from scribe minus to the scribbles, the phi out modes.
Yes, that's exactly what we're going to do.
But there are some modes that will fall inside the graph.
Yeah.
Why are you not considering them?
I'm going to choose, I'm choosing scribe minus as a shape surface.
Fine.
And beta is the product between in and out, not including Q. Q is the modes that have support, that fall into the black hole, if you wish. Support H plus, not into high plus. I'm not considering them because we are observers at Sky Plus. We're going to see what happens here. And not just at Sky Plus, but at Sky Plus for large U. That's who we are. We're people here. In fact, we're not null observers. We're not having a null. We're something that asymptotes, that goes to I plus. It's extremely close to Sky Plus. That's who we are, where we are. So we're not observers inside the horizon, that's why we're not in Q, we're interested in phi out. That's phi out is what defines the vacuum state of Sky Plus. Our vacuum. So we need to find phi out at Sky minus. We know that Sky plus would find at Sky minus. This is purely outgoing to Sky plus and it's 0 with H plus. And we're going to look at this at late times, meaning as U goes to infinity. We want to get we are observers at late times. We want to see what happens after the black hole has formed. So this means near C0. And we're going to trace it back from Sky plus to Sky minus. See how what the form is. So we know that it's 0 here. We know that it's an outgoing wave to sky plus. We are close, we're close to the horizon, to C0. What's the value of the field phi here? If you trace this back, what's the value of the field at a point near the horizon?
That mode, you should use the expression wrote for u as a function of v.
Sorry, can you say that?
You wrote an expression u as a function of v. You should use this expression. You should use.
So before, that's going to be important later on, but before we get into that, what's the form of phi? We don't even, not even phi out. What's the form of phi? Sorry, there's one. So we want to be near the horizon. Yes. So what? What's here?
The multiplier because u is going to infinity.
Why does it go to 0?
Because u is going to infinity.
Yeah. So why does this go to 0?
Because it's minus.
It's minus I. So this
This is why.
time is here for it. Anything else? Is it just this? I'm missing factors here. Let's go. Let's say that this is, we really want our exponential of minus I omega t. The rest plays no role. The angular function, all this bit plays no role. This is innocuous. It has no physical content. Let's just concentrate on our exponential minus I omega. So we have this. Anything else?
Let's say use the phi u.
Okay, meaning what?
The limit that is hard is close to infinity.
We're not near infinity. We're near the horizon.
Yeah, it's goes to the horizon there. It is
What's the solution of R near the horizon?
the horizon. That makes an exponential. Just
My students should know this inside out.
R is the radial part.
Yes.
Should be. I think it might be proportional to the exponential of I omega v.
I
Omega v.
omega.
V.
So V contains T. This is just R.
exponential of minus I omega r star. I'm sorry.
Okay. Good. Anything else?
Well, it should be going to the horizon. So this is
Why should we go to a channel solution? A channel solution of the radial equation.
that is something exponential of I omega.
Some function of u minus v.
U and V. Okay.
Exponential of plus I omega r star.
Exactly. It has two. It's a second order of E. It has two linear independent solutions. That's just So from coefficients, you use schema as R star. So I've switched them. So this really should be A and this should be B. Okay, that's the general solution. Now, this is true close to the horizon. For the particular case of phi out, we don't have a B term on the horizon. But we do just a little bit away from the horizon. We don't have that at C0. We do have a term like that at C1. So our out, it's near H plus, but not on H plus, because the boundary condition for phi out, let's do this for phi out. So this is y's and m's. This is not true on H plus because phi out has been defined to be 0. To have Cauchy, 0 Cauchy data and to be 0 on H plus. So on H plus we don't have that. A little bit farther away from H plus we do have that. So what that means is we've got a guy, this guy is dA, and we've got some guy coming in here, some b exponential of minus omega v. Now, this guy does not cross the horizon. This guy is not going to cross the, this is non-existent on the horizon. Okay. This might sound strange, but it's not. If you, especially my students, if you think of, say, there's an ingoing solution, which is like this. You know, in here, if you look here, it has 0 Cauchy data, but just outside it, it has an outgoing guy. But just on it, there's nothing coming out of it. If this is like this, there's nothing coming out from H minus. But just outside H minus, so there's no this here, but just outside H minus, there's a wave. So similarly, phi out is kind of the reverse of this. Phi out is this. It has an outgoing wave from here, if you wish, an outgoing wave from sky minus, outgoing to sky plus, but nothing on H plus, and so nothing is going through H plus. But just outside H plus, we've got the two waves. Did you confuse a bit? Which bit don't you understand?
Why exactly isn't this e to minus I omega v going inside H plus?
That's our definition of, I've defined phi out to have zero Cauchy data here and to be an outgoing wave to square plus. But if you are just outside it, you've got two waves.
So there is. Okay.
Maybe it's easier. It's the reverse of this. Think of it in a different way. Think of it of another solution, the in solution. This is what we call phi in. Phi in was defined to be, okay, just here I'm giving, this is Schwarz, this is the maximal extension of Schwarzschild space-time. Okay, this is not quite, this is on the room. So in that space-time, just outside Schwarzschild, let's forget gravitational terms. Just outside Schwarzschild, you've got you can define a solution to the Klein-Gordon equation which has zero Cauchy, it's zero at h minus, and it's a purely outgoing wave at square minus. Okay, I think that's my choice. I choose initial data, my initial data is this. And now I evolve that initial data. What's going to happen? There's zero, nothing is coming out from h minus. Okay? There's no this at h minus. But just outside h minus, I have this guy. This is exponential minus I omega v is everywhere. Okay, this is just a wave coming out from sky minus. And it's reflected because of the interaction with the radial potential. Some transmission guy and some reflected guy and some transmitted guy. Okay, there's backscattering due to the gravitational potential. So some of it is backscattered. This is coming out from square minus. Some of it is transmitted through. Some of it is reflected. That's happening everywhere. That's happening just outside H minus as well. Just outside H minus, this is happening. But you still have zero data at H minus, outgoing wave at sky minus, just a little bit outside H minus, you have the backscattering. So this is what we're doing here, just a reverse, time reverse of that in some sense. We've got zero, our definition of Cauchy initial data, which we put at t equals infinity, plus infinity, is zero data at H plus, outgoing wave to sky plus. Where is this coming from? Well, is this coming from guys here? From guys here, this backscattering, if you reach this backscattering, everything just outside H plus, there's backscattering, and you've got the two waves. But on H plus, you don't. They annihilate. In some sense, you can think of it, if you wish, as this guy cancelling out this guy just on H plus.
Would be something like defining initial conditions on sky plus and evolving backwards.
Sky plus and H plus, and evolving backwards.
So but there should be no Cauchy data on H plus.
Right, that's our definition of phi tau. You could define another solution which has Cauchy data coming out H plus. Right, but we're not. In fact, this one does. Phi has wave coming out H plus, a wave coming out to sky plus. But we're not, phi out is not defined like this. It's a phi out. It has zero Cauchy data on H plus. Okay. This B guy is just a reflected wave. It's the one from backscattering. It's this guy here. It's due to backscattering. We're not going to consider this for now. Later on, I'll tell you how you have to change the result in order to include this backscattering. But this backscattering is quite innocuous. It does not really give you the thermal factor that we're seeing. And this is the backscattered wave. ignore for now. Later, we'll introduce its effects. It doesn't play a role in the terminal character of the cognitive relation, so we're not going to ignore this guy. So we're going to trace back this guy. We're kind of ignoring this. Later on, I'll say what the inclusion of this, how it would affect the result. We're going to trace this back. This is at sky plus. We're tracing it back to H plus, and we want to trace it back to sky minus. First question: as it goes from sky plus to H plus, is it red shifted or blue shifted?
The mode is going from sky plus to H plus.
Blue shifted. So that's correct. As a wave comes out of the horizon, it's getting red shifted. As it goes towards the horizon, it's getting blue shifted. So we're going backwards. We're tracing it backwards in time, if you wish, from sky plus to sky minus, and it's getting blue shifted as it approaches the horizon. So the frequency of phi out as locally measured by an observer that is freely falling. Free falling observer at H plus or near H plus so it's blue shifted, so the frequency is largely grows largely infinite blue shift. As you approach the horizon, it becomes infinite blue shift as we approach the horizon. Now, you can see this by, so you can see this, remember the no geodesic C is a geodesic, so it's free falling going to the horizon. When we say observer, we mean something that, so an observer cannot be at C, because C is null geodesic, but it can asymptote. So by an observer, I mean the slightly loose terms here. I'm talking about. I'm going to talk about this in relation to a fine parameter lambda along C. Okay, so that's what I mean by an observer going into the horizon. So C has a time parameter lambda, and we know that u lambda, as lambda goes to 0, is this. I'm just writing what I wrote yesterday. And this is the phase. So here, this thing here, I call it capital S. This is just the phase of the wave. Phase of the wave. So now, so the point is the following. When we say the frequency is locally measured by a free-falling observer, by free-falling observer I mean with respect to the defined parameter along C, is blue shifted by frequency. That frequency is not omega. It's the frequency as seen by that observer. Okay, omega is with respect to T, which is an observer at sky plus at R equals infinity. Now we're not saying with respect to T. We're not saying with respect to an observer at infinity. Frequency omega is a frequency with respect to T, which is the proper time of an inertial observer at infinity. We're saying with respect to the proper time, or in this case, it's an is a defined parameter along C. So what we really want to know, what we want to get, is ds d lambda. I'm not talking about ds dt. That would give you the frequency with respect to an observer at infinity. We're talking about an observer with respect to C. Okay? An observer near H plus and with respect to C. The defined parameter along C. So df d lambda. So that goes. So as is omega u. Okay. And u goes like this. Differentiating with respect to lambda gives you something that goes like 1 over lambda. As you approach the horizon, this goes to infinity. Okay. So this is, I'm just mathematically justifying what I wrote down in words, or making more explicitly what I meant. Okay. By this frequency, I meant this guy. Now, what that means is that we can apply geometrical optics. This was the insight by Hawking. People thought this calculation would be too messy, too hard to do. This was the insight by Hawking. We are seeing waves here, which, with respect to our proper time, have order one. The magnitude of the magnitude of the frequency of the wave that we're receiving. Frequency with respect to our proper time is unity, but those waves, when you trace them back to H plus, have got infinite frequency with respect to a local observer. Okay? They're infinitely blue shifted as you go there. And so you can apply geometrical optics. When you apply geometrical optics, that basically means that they follow null geodesics, that the wavefront of those waves follow null geodesics. A little proof of this. I mean, you can find this in many places. So, by geometrical optics, so we've got phi out. It's a homogeneous solution of the time order equation, and then that gives you that this. If you plug in the value for phi out, if you plug in this, so that tells you that the normal to S, the normal to the hypersurface with S equals constant is null. Okay, that's so this means that S equals constant are null hypersurfaces. C0. And this is because if we define the vector k, which is this is really ds, capital S. This is a vector that's normal to the s equals constant hypersurfaces. S equals constant hypersurfaces means U equals constant hypersurfaces. U is along here, so these guys are S equals constant hypersurfaces. ds is perpendicular to that, so this is, and ds is parallel to k mu, covariant, k mu contravariant is tangent, it's a vector tangent to the s equals constant hypersurfaces. Because it's null, since this is a normal vector to s equals constant hypersurfaces, and it's null, and it's null. So k mu is a normal vector. K mu is a tangent vector field of null geodesics. It's a null vector. So what do we have? We've got a wave near Skypos at late times u, and it's got it's a wave like this, if you wish. So here I'm plotting S, capital S, is a function of u, and it's a wave, okay, of unit amplitude, of unit frequency. Frequency with respect to u, okay, this phi out is exponential of minus I omega u, so omegas of order unity, so the frequency with respect to you is just a happy, normal frequency, order unity. But that wave is blue shifted as it goes from sky plus to H plus. So if you look at, this is my C, now you plot this wave here, this capital S, and in here I plotted, this is a plot with respect to the affine parameter along C. Here I'm plotting it with respect to the affine parameter along H sky plus, which is U. Now in here I plot with respect to the affine parameter along C, which is minus lambda. And it's been infinitely blue shifted. So for some value, this some value U equals constant. In here it's been largely blue shifted. So in here you have a very, 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 very high frequency with respect to the local fine parameter. Okay, and now these geometrical optics tell us that it just, so this is a very large local frequency, and so we can apply geometrical optics. That means that the wavefront follows null geodesics. So that means that this just follows null geodesics. So you have exactly the same blue shifted frequency here. If you plot as a function of V, you have the same equally blue shifted. If you plot it with respect to the affine parameter along sky minus, which is V.
Would it imply that a wave is, when it's going from sky minus to sky plus, if it has a small frequency at sky minus, by tracing it towards sky plus and going back, we'll have infinitely low shift effectively. But shouldn't it be the same wave when you go back to sky minus? Suppose that you have a wave with a very small frequency at sky minus, and then you evolve it towards a sky plus. By going back and following this reasoning, we will conclude that our initial wave was a very, very blue shift, a very high frequency wave.
So you start with a very small frequency wave at sky minus.
Yes.
Okay, now you evolve it here and get something
If I
tiny.
Yes. With a very high frequency. Due to the blue shift.
If you start at sky minus with a really small frequency, if you start with something with a very large frequency sky minus, basically the horizon hasn't been formed here as the wave goes in inwards. It is formed as it comes out, as the wave is coming out. It reflected out from R equals 0. So from sky minus to here, there is no massive redshift nor blue shift. The horizon hasn't been formed. As it's reflected and the horizon forms, the wave is near the horizon, the null generator of the horizon, then that wave will experience the very large redshift as it comes out, as it goes out to sky plus. It will experience a very large redshift. So if it started with a very large frequency, at sky minus it will still have a very large frequency as it's reflected, but it will be largely redshifted until we have an order 1 frequency at sky plus. If you start with a really small frequency square minus, it will still have a really small frequency as it's reflected, and it will have a tiny, tiny, tiny wee frequency at square plus.
And I'm sorry, why the affine parameter is minus only now? Because it was approaching 0 as we approach H plus.
So it should be lambda. I wrote down minus lambda because lambda 1, I meant minus lambda 1 because lambda 1 is there. Or, yeah, it doesn't really matter. So this is lambda, sorry. I wrote down minus lambda because lambda is negative before it reaches H plus. So,
Just
this point
because
is
it's approaching the 0 for on the left.
yeah. This minus is not always what really matters is infinite, as we trace it back from square plus to square minus, infinite blue shift as it close to the horizon. Every time I say blue shift and red shift, I'm talking about frequencies. Every time I talk about frequencies, I mean local frequencies, as measured by a free-falling local observer. Free-falling, inertial, free-falling local observer at sky plus. Sky plus is flattish, it's an inertial observer. Its proper time is t-ish. Okay, I'm switching all the time between t and u. I'm thinking of an observer, time of observer extremely close to almost not an observer. And similarly here, I keep switching between a null geodesic C or an observer, a time observer. So when I say time, it's not really time, it's a defined parameter. If you can think of it either as an observer, either as kind of sort of a proper an observer very close to that, or else I think the right mathematical way of thinking about this is not an observer, but a null, an affine parameter along the null geodesic. So u being an affine parameter along this null geodesic, v, what is this? V being an affine parameter along sky minus, lambda being an affine parameter along c. So frequencies with respect to those times imposed, they're not times because u and v and lambda are null, u and v are null coordinates, but as a loose language, we say they're times. I mean, maybe you find it easier to not think of it in terms of Penrose diagrams. You've got now just an RT diagram. You've got the surface of the star. So this is star and T diagram. Surface of the star. It's at some radius which keeps decreasing. I'm doing X as opposed to omitting Y and Z. There's factor symmetry anyway. So the surface of the star is just decreasing until, and then at some stage, so some way, first of all, at r equals 0, there is a singularity. Secondly, at some stage, so there's no rays coming out from sky plus. One of them is such that, so some of them will escape and will reach sky plus. One of them is such that it will continue at r equals constant value, r equals 2m. That's the null generator. This guy is the horizon, the null generator of the horizon. And similarly, this is totally symmetric. So this guy, there's one coming in from x equals minus infinity as well. And similarly, this is totally symmetric. And ones that will escape out to sky plus. Now the point is, they're getting, that's a way of visualizing the redshift as they go to the future. Here they're very tight, they're very close together, but as they evolve to the future, their separation increases. We're getting redshift as they come out to the same thing here. So that's another way, non-conformal diagram way of looking at it. So we can apply geometrical optics all the way from near H plus to sky minus. There's a certain redshift as you go, or blue shift, there's a certain change in the frequency as you go from H plus to sky minus. But that's just a linear shift. Remember I told you on Monday that the delta, it's showing here, there's a linear shift between lambda 1, so the defined parameter separation along C, and defined parameter of separation along sky minus. Lambda 1 is V0 minus V1 divided by K2. So there's a K2 factor, there's a linear factor of shift in frequency. Okay, lambda 1 is V0 minus V2, V0 minus V1 divided by K2. So that gives you certain shift. The point is, it's not an infinite or extremely large redshift or blue shift. It's just an infinite, it's just a finite, it's a linear shift. In going from here to here, that's not a linear shift. It's logarithmic if you go from V to lambda. It's exponential. Exponential if you go from lambda to V. It's not linear. This one is linear, and this plays no role. This doesn't affect. This will give you thermal character of Hawking radiation. This makes no difference. So propagation, just as just right now, will it just say propagation through the star? And from entering the star down to square minus only brings a finite or linear shift. And this is if you want to, you can do this as an exercise. So giving you exercises, things that you can practice with. So, in other words, we can apply geometrical optics. So each wavefront by which I mean S equals constant hypersurface will follow null geodesics of the spectrum. the space-time, what's the space-time? Well, the space-time is Schwarzschild outside the star. It's dynamic, crazy, messy inside the star. It's not static, it's dynamic inside the star. That is really what's giving you the creation of particles. There's a dynamic, it's a dynamic space inside the star. But we don't care about details. The only details about that, about the star, are in K2. Okay? And then it's Schwarzschild again as you come out of the star as you approach Skybrains. So this means that phi out at near sky minus will be like this. This is for V. And V0 is this guy here. For V larger than V0, the wave just falls into the black hole. So for V larger than V0, this is just 0. They're all accumulating. So this is V equals V0. For V larger than V0, they just fall into the black hole. They don't come back out to sky close. And the relationship between this U, this function of U as a function of V, is just given by this as V approaches V0 from the left. So this is the value of U, the U coordinate along C. Any questions with this? I forgot to bring my clock. Okay, so now we've got phi out at sky minus. We already know phi in at sky minus, and so we can calculate the scalar product. proportionality sign here, so I'm ignoring here normalizations, angles and so on. I just want to do something heuristic. Whenever we calculate the Bogoliubov transformation coefficients, in the case of Ringler, we did it in a smart way. In the smart way that Umbro came up with. In here, we're not going to do it in a smart way. We're going to do it in a laborious, stupid way. Now, but can we go back to that thinking of the way we did it for Ringler? First question. Are these analytic in the lower V-plane?
It is analytic.
Why?
The exponential of analytic function.
Yeah. It makes a power series anywhere, and so that's what it means. Is it bounded in the lower U-plane?
It must have an imaginary part that is smaller than zero.
Is it bounded in the lower U-plane?
Yes.
Yeah. Because V in the lower U-plane will be minus I times something positive. Minus I times minus I is minus omega positive U minus I minus something positive is something negative, and so this will become, as V goes to infinity, the lower U-plane will go to zero. So it's analytic and bounded. What about phi out? Is it analytic in the lower U-plane and V-plane? If this analytic are bounded in the, sorry, when I said U-plane, I meant V-plane instead. Well, U-plane obviously it is because there's no independence. Is it analytic and bounded in the? Is it analytic in the lower V-plane?
It is analytic in the lower U-plane. Now we have
The deep plane that is,
Is that in the lower V-plane?
I cannot say this because that is the lower Newton function itself.
I mean, already you can tell it's zero up to some value of V, and then it's not zero anymore. So that cannot be analytic. It's discontinuous and V equals to zero. It's not this. So this means that you cannot take a linear combination of these guys and the complex conjugates of these guys. You cannot take a linear combination of these guys to form these guys, because any linear combination of these guys would be analytic. Now, phi and phi star form a complete set, so you can definitely you can express phi out as a linear combination of phi and phi star. Now, once you include phi star, that will give you, in principle, that will give you a beta, which is non-zero and so particle production. Okay. We're not going to do it this way. You could do it the way Onward did it, applying to the black hole case. We're going to do the pedestrian way. So beta this, we choose Cauchy surface to be sky minus. Sky minus is this guy here. It has u equals constant, and so the u is perpendicular to that. So the sigma is parallel to the u. Okay, sigma must be perpendicular to the normal to the Cauchy surface, and so this means that d sigma mu must be